Hello, welcome to today's lesson. Today's lesson is going to be on the topic of inverse functions. If you're in the Unified class or Pre-Calc Enriched, this is section 1.6 in your textbook. If you're in the Period 4 Pre-Calc class, this is the section 3.6 in your textbook. So what we're going to do is we're going to talk about inverse functions. And I'm first going to start with just one example of a pair of inverse functions. And we're going to go through how we can tell that they're inverses graphically from their graphs, numerically from the points on the graph or a table of values, and algebraically from the equation. So first, graphically, if you have a pair of inverse functions, the graphs will be reflections of each other over the line y equals x. And for this pair of inverse functions, for this example that I've selected, we actually can graph these by hand because we know our basic cubic function and we know our transformations. We know this is moved down 5. So I'm going to go ahead and sketch my basic cubic function moved down 5. I'm going to label that F, and I'm going to grab a different color for G, because why not? And this is our cube root function moved left 5. So the cube root function moved left 5 looks like this, and it goes down to the left. And if I've done my drawing pretty well, which I'm pretty pleased with here, if I put the line y equals x in, these two graphs should be reflections of each other over the line y equals x. And y equals x is a line that you're going to see repeatedly throughout this course, and that's the line that goes straight through the middle of quadrant 1 and straight through the middle of quadrant 3. So these are mirror images of each other over that line, y equals x. And notice where they intersect is on the line of reflection as well, just to be aware of, because you'll see that in many of the examples that we're going to see. So that's what happens graphically if you have a pair of inverse functions. Numerically, what happens is any point that you have on your function, the ordered pair where you've swapped the positions of x and y will have to be on the inverse. So we can take a look at some examples of points. So for example, if you notice, you have the point 0, -5 on F. Do you notice that you have the point -5, 0 on the inverse, which I'm calling G here? So that's going to happen with every pair, every single point on the graph of F. If you swap the positions of x and y, that other point has to be on the inverse. And I have another example of that. So another example of that, let's say we go here and we plug in 2. So plug in 2 for x in the function F. You'll end up with 8 - 5, which is 3. So if that point is on F, then what point has to be on the function G? Well, 3, 2 better be on the function G if it's the inverse function. And sure enough, if you plug in 3 here, 3 + 5 is 8, and the cube root of 8 is 2. And that happens with all the points on the graph. I just picked these examples because they're nice integer numbers. I don't want to get involved in having something like the cube root of 6. Because like if I plug in 1 here, I'll get cube root of 6. So if that point's on G, then if you switch the x and y, that point has to be on F. But that's just going to be a little extra confusing in my opinion because it's an irrational number. So I thought I'd just show you the basic examples with some nice integer values. And then here's what happens algebraically. Here's what happens when you have the equations. When you do a composition, whether you do f of g of x or g of f of x, they both come out to x. That's how you can verify, or that's how you can tell that you have a composition of functions. I'm sorry, that you have inverse functions. So let's go ahead and show that here. So we can algebraically show that these are inverses by doing f of g of x, and then we're going to do g of f of x as well. We're going to do both compositions. So for f of g of x, you guys, I've shown you 2 different ways to kind of do the compositions in class. So it's up to you how you want to show that you're going to plug this expression in for x right here. I showed 2 ways to do that in class. You pick your favorite method and you stick with that. And what you're going to have is you're going to have this function g of x is going to go right in place of x. So you're going to cube it and then have a -5 on the end. So if we simplify that, we are going to cancel out the cube root and cube. You can't do the 5 and -5 first because the +5 here is trapped inside the cube root and trapped by the cube. So you do have to cancel out the cube root and cube first. And that's going to leave you with just x + 5 - 5, which leaves you with just x. So we got, as we expected, the first composition came out to x. And now we want to see that should happen over here when you do g of f of x instead. So once again, you pick your favorite method for evaluating g of f of x. So this is going to end up going right in place of x here. So whichever way you prefer to show your work, or if you're comfortable jumping to this step, that's fine as well. So that's what I've replaced x with. And then I'm going to keep that plus 5, and I'm going to be careful that my radical contains the plus 5. Now notice in this work, you had to cancel out the cube and cube root first. Over here, you cannot cancel out cube and cube root first because these plus 5 and minus 5 are in the way. So for the work for this one, you need to cancel out the 5 and minus 5 before you cancel out the cube and cube root. And since both come out to x, we have indeed verified or proven that we have inverse functions here with f and g. All right, now that we've reviewed from Algebra 2, for those of you in the pre-cal class, you did this last year in Algebra 2. In Unified, I believe this is a new topic for you. We're going to go ahead and apply what we just learned or reviewed. So taking a look at these examples, I have 3 different sets of graphs here, and I want to know which appear to be inverses of each other. So if you're looking at the graphs, what you want to do is you want to think about the line y equals x, or actually just draw it in. So if you draw in the line y equals x, it goes through 1, 1, 2, 2, 3, 3, 4, 4, and so on. And these appear to be reflections of each other. So these appear to be inverses. So I didn't label them. If you want to call this A and circle it up, feel free. Then we can investigate B and C, or you can just write down that they're inverses. Okay. For this example, if we put in the line y equals x, the y equals x line goes through 1, 1, 2, 2, 3, 3, and so on. It goes right through the middle of quadrant 1 and quadrant 3. The blue and red graphs here are not reflections of each other over the line y equals x. So these are not inverses of each other. They do intersect, and they kind of look like they had the potential to be inverses because they are reflections of each other. But in order to be inverses, they have to be reflections over the line y equals x specifically. All right, and if we check out this last example, if we put in that line y equals x, these do appear to be inverses. Their point of intersection is on that line y equals x. This appears to flip over and be a pre-image and image here. These are mirror images of each other, and these two parts are mirror images. So it looks like the first example and this third example are pairs of inverses. Okay, next, for number 2, if the point 3, -4 is on the graph of a function, what point has to be on the inverse? Well, we switch x and y. You're going to hear me say switch x and y a bunch of times when we're talking about inverses. Sometimes I even say, to help myself remember, inverses are all about switching x and y. All about switching x and y. So if we just flip-flop the ordered pair, we don't change any signs or anything, we just reverse the x and y, that point would have to be on the graph of the inverse. Okay, continuing on our way for more applications of what we just learned or reviewed. Okay, I have 2 examples where we're going to do some algebra down here. So we want to determine algebraically whether these are inverses of each other. Okay, when you look at them, it looks like they have the potential to be inverses because you see you have times 3 and you have times 1/3 or divided by 3. Those are inverse operations. -5 and +5 are inverse operations. But we don't want to just look and assume, we really want to verify. And we're told to do that algebraically here. If we weren't told algebraically, we could just graph them and find out. But we want to determine algebraically. So when you see those instructions, you want to find the composition. So I'm going to start with f of g of x and see if it comes out to x. So what we're going to do for f of g of x is we're going to take g of x and plug that right in here instead of x. So I'm going to have 3 times this quantity. And pardon my 1/3 here, that's supposed to be 1/3. And then if I go ahead and try to simplify this, 3 times 1/3 x is just x. And 3 times 5 is 15. And 15 minus 5 is not going to cancel. So we're left with x plus 10. And since the composition did not come out to just x, we know that these are not inverses of each other. We don't even have to test the other composition, g of f of x. If the first one you do doesn't work, then it's no good. They're not inverses of each other. And it looked like they might have been. So be careful because it's easy to get fooled by the equations. Okay. So because the first composition I tried didn't come out to just plain old x, these automatically are not inverses, and we can go to the next problem. Okay, so number 4, take a look at these. Just curious, do you think they look like inverses? I have times 1/2 and I have times 2. So I have times 2 and divided by 2. That looks pretty good. Those are inverses. Plus 2 and minus 4 are not inverses though. So I would say if I were to look at this, I would think that they're probably not. But we don't want to just look and guess. We really want to verify whether or not they are. And so since we're doing this algebraically, we're going to do the composition f of g of x to start. So we're going to take g of x, plug it right in here in place of x. Since it's 2 terms, I have to use parentheses like I did in the last example. All right, so I replaced x, and then I keep the plus and I keep the 2. So when I distribute the 1/2, I get x minus 2 plus 2. And sure enough, this comes out to x. Now, to fully verify or determine algebraically that we have inverses, I'm going to ask us to find g of f of x as well. And often students will ask me, like, but hey, if the first one comes out to x, do I really have to do that work for g of f of x? Yes, please. Now, for all of our examples, if the first composition comes out to x, for all of our examples, it's true that the second composition is going to come out to x as well. But technically, in order to really prove or verify, I do need you to actually show both compositions come out to x. So even though you may not want to do it, that's going to be part of the expectations if you're determining algebraically whether you have inverses. So to determine algebraically whether you have inverses, we are going to do g of f of x. So we're going to take f of x and put that right in here in place of x. So I kept the 2, and then I put 1/2 x plus 2. And then I kept the minus and the 4. Careful with parentheses, as always. And sure enough, this one comes out to just x. Oop. Little malfunction there of my tablet. Let's try that again. And sure enough, this comes out to x. So we do indeed have inverses. Okay. So you can write, I guess you could write yes. It wasn't really a yes or no question. I'm just going to write f and g are inverses. You could just write the word inverses. That would suffice here as well. Okay. So the next thing we're going to do is we are going to now take a look at how to find an inverse equation. Okay. Whoops, you weren't supposed to see that graph yet. Okay, how to find an inverse equation. So in order to find an inverse equation, what we want to do is we first want to look at the graph of the function that I'm asking you to find the inverse of. Because as it turns out, not every function has an inverse function. So before we try to find the inverse function, we want to look at the original picture and make sure that it has a characteristic which is called 1-to-1. We want to make sure it passes the horizontal line test. Okay. So this might be new to some of you, even if you took algebra 2 instead of unified. If you're in unified, this is new. If you are in pre-calc, this might be new because you're not sure if your teacher did this part last year. Okay, so what I did is I went to Desmos.com and I graphed this function right here. Okay, it is a function because it passes that vertical line test. What we want to do is we want to find out if it passes what's called a horizontal line test. So you want to envision or draw horizontal lines throughout the graph. If it hits the graph once or not at all, that's cool. But like right here, this horizontal line hits the graph 3 times. That is no good. We just failed the horizontal line test. So it works the same as the vertical line test. It's just with horizontal lines instead. So this failed the horizontal line test. So if it fails the horizontal line test, as it says in the instructions up there or in the notes, then the inverse is not a function, and you can just go to the next problem. So if you end up with a graph that fails the horizontal line test, if you can find even one single horizontal line that intersects the graph at more than one point, you get to just say no inverse function and move to the next problem. Now, of course, I'm going to extend on that just a little bit to explain what we're finding here. So the inverse of this does exist. I went on Desmos and I graphed the inverse. So here's the red one. That's the one we were just talking about. And the blue one is the inverse, because if you flip over the line y equals x, the red one becomes the blue one becomes the red one. So the inverse exists, but focus on that blue graph right there. There's a problem with it. There's something we don't like about it. And what we don't like about it is that it's not a function. Let me show it to you on its own. If you take a look at this and you try the vertical line test, this fails the vertical line test. So this is the inverse of the red graph. The inverse exists, okay? I'm not saying the inverse doesn't exist, but it's not a function. And in our math classes, we're kind of obsessed with functions. We like everything to be a function. All right. So since the inverse is not going to be a function, we say, okay, don't even bother trying to find the equation. All right. So that's what's going on there. All right. Let's continue on to our last example. Okay. So I just copied and pasted this so we could have the instructions up here again. And so what we want to do is we want to look at the graph of this function. If we want to try to find the inverse, we want to look at the graph first. And I don't think we need Desmos for this one. This one's just a linear function. So it's a y-intercept of 3 and a slope of 2. So from here, if I go up to right 1, up to right 1, I'm just sketching it because we just want to make sure it passes the horizontal line test. So let me go ahead and switch colors. Okay, so it's a function because it passes the vertical line test and it passes the horizontal line test. No matter where I put a horizontal line, each input has, each horizontal line only passes through the graph at one point. So this is a function because it passes the vertical line test. And since it passes the horizontal line test, it's what we call one-to-one, which we will discuss further in our next lesson. And if it's one-to-one, then that means that the inverse will be a function. So when we find the inverse itself will be a function. It will pass the vertical line test. So since we now have established all of that, we can go ahead and find the inverse. So the function passed, so the green one passed the horizontal line test. We can find the equation of the inverse. Here's the process. We start with our given equation. Okay. We replace f of x with y. And different teachers teach this next part differently. The way I like to do it is right now I switch x and y. Okay, and then solve for y. So we want to get y by itself. So I'm going to move the 3 over by subtracting it. And then I'm going to move the 2 over by dividing it. And that's my inverse. Now, just to get fancy in practice notation, what we will often do is use a notation for inverse that says f inverse of x. It looks like f to the -1, but it is not the exponent. It is it's written the same as like a -1 as an exponent, but what it stands for is the inverse of f. Okay, so we read that f inverse. So this is f inverse. And we're going to start to see that notation more as we continue our practice with inverses. And if you wanted to, by the way, if you want to make this 1/2 x minus 3 over 2 by splitting apart that fraction, you could, because then you'll recognize that this is just a linear function as well with a slope of 1/2 and a y-intercept of -3/2. Final thing for this example is I did prepare the graph for you just in case you wanted to see it. And that graph looks like this. So here is the original f, and here is f inverse. And they are, sure enough, reflections of each other over the line y equals x. And so we found the correct inverse. All right, thanks for watching, and get you some more practice on all of these skills as we continue in the next couple days.